Thank you. See, sometimes my working memory, not as good. Uh, and so anyway, so our working memory, it can contain information, like I said, that comes into our mind from the environment. Um, or it can also be made up of information that you've pulled from long-term memory. So an example of this is like if you were to go and like visit the carpet store. I don't know if there are specific stores just for carpet, but say you're shopping for carpet, and you're looking at the carpets, and then you're remembering, okay, what are the measurements of the living room that I made again? So you'd have to pull those dimensions in, whatever those measurements are of your living room, into your working memory. And then you'd have to multiply them to figure out, okay, how many square feet of this carpet do I need, right? Because the carpet's going to come in square footage. So that's the measurement. That's what you're having to figure out. And so in each of these cases, whether it's someone asking you to, hey, can you do this mental arithmetic, or you trying to solve a problem based on information that you already have, working memory, it contains information that can be acted on and processed. So it's not merely something that is just holding on to information just by rehearsal, just by saying it or thinking it over and over again. Although that rehearsal, that maintenance of information, it is an important part of working memory, but it's not the only way in which it functions. And so the term working memory, it was coined by a cognitive researcher named Alan Badley. He's a pretty big deal in cognition, so you'll hear his name come up pretty frequently, especially as we're talking about memory. And so he and his research partner Hitch, they argue that the idea of short-term memory, as it was conceptualized in that modal model, it wasn't enough. It was too simplistic. There wasn't a way for it to explain how we are able to not only maintain information but also process it over short periods of time. And so in order to develop a better model, they started conducting studies to try to see if they could flesh out a little bit more of what's going on in short-term memory. And so in the study, they presented participants with a string of random numbers that they then had to rehearse in order. So they had to hang on to it, both in terms of what the numbers were and then also the order that they were in. And so as they were rehearsing these, let me back up. So this string of numbers, it varied. So it was either 0 items, which is probably nice to get those to be like, okay, on this next trial, oh, you don't have to remember any numbers. Or memorizing 8 numbers in order. And so again, sometimes the participants, they didn't have anything that they had to rehearse, right? There was nothing that they had to hold and rehearse in working memory. And then other times they had a much longer list that also really kind of pushed the boundaries of human short-term memory. Going back to George Miller's magical number 7 plus or minus 2, 8 numbers is really pushing the limits. That's really difficult. And so as these participants were rehearsing number strings, they were also required to work on a spatial reasoning task. And so what this task looked like is they had to make judgments about whether statements were true or not, about the order that letters were in that were shown to them. So for example, if they were shown the letter combination B-A, so B and A right next to each other, if the statement said B follows A, then they would, well, a correct response in that case would be selecting no, that's not correct. But if the statement said A follows B, then they would push a yes button. And so all the research that we've looked at should suggest that performance on these two tasks should be really hard, and people should make a lot of errors. But actually, what Badley and Hitch found was that participants were like amazingly fast and accurate on both tasks. And so there wasn't a big difference between the trials in which they were rehearsing no digits and 8 digits. So there's no difference there when it came to them making correct spatial judgments. And so, and the error rates too were really low. The error rates were 5%, regardless of how many numbers the participants were rehearsing. So they were correct 95% of the time when they were making these spatial judgments about letters, regardless of what was going on in their working memory at that time. And so this research then, it called into question Miller's argument that we have, 5 to 9 slots essentially in our working memory. And it also called into question the idea that we can only process information in a serial manner, so one after the other, and we can't do parallel processing. So this sort of idea of juggling or processing multiple pieces of information at once. And so in light of this research, Badley and Hitch, they proposed this 3-part working memory system. And based on their research and their theorizing, they said that they thought it consisted of what's called a central executive mechanism that would then be involved in controlling 2 subordinate or lower systems. And this is called the phonological loop and the visual spatial sketchpad. And each of these sort of subordinate structures under the control of the central executive corresponded to a certain modality. So the phonological loop, that was for auditory information, and the visual spatial sketchpad, that was for visual information. And Badley eventually added a 4th component later on called the episodic buffer. And this was to help really further nuance some of the complexities of this working memory model. And so the way that Badley conceived of working memory is it's this multi-part system that temporarily holds and manipulates information as we're going about doing different tasks. And so this then really emphasizes the idea that working memory, it's not this sort of simple storehouse, right? Like the short-term memory idea in the modal model. It's not just, you're not just throwing things in there, they're sort of partially processed, and then you can come back to them later and then keep processing them. But rather it's this idea where it's more active, kind of like a workbench or like a desk, where materials are constantly being added and subtracted, manipulated. You're taking these different tools and you're working on whatever that project is, building it, deconstructing it, etc., combining pieces, transforming pieces of information, and things like that. And so for this next part, we're going to watch a video that I think gives us a really nice overview of the function of working memory, as well as its various parts. And then we'll continue really discussing them in more detail. So.
Working memory is a specific type of short-term memory that processes language and perception in the brain. Specifically, this memory allows us to manipulate objects, items, and numbers in our brain to perform complex tasks. So working memory is one of the 3 main executive functions that help people organize tasks, regulate their emotions, and pay attention in the moment. If you're a fan of meditation or mindfulness, working memory is crucial to these activities or state of mind. To better show what working memory is, I'm going to give you a short example. In a TED Talk, Peter Doolittle asked audience members to memorize a set of 5 words. He then gives the audience a multiplication problem and some other simple tasks to complete. If the audience could remember the 5 words after those simple tasks, they could congratulate themselves for a high working memory capacity. And if you finish watching this video, I'm going to give you a simple test too. Once we decide to draw our attention to a sensory input, like something we feel or something we see, it then goes into our central executive memory. Now, this is the manager of the operations that working memory completes. The central executive memory system delegates tasks to 3 simple systems. It decides what input is most important, what parts of the working memory system will handle the information, and what ends up continuing the process into long-term memory. So before I continue, psychologists know the basics of what central executive memory does, but the process in which it is done isn't so clear. For example, you might know that a car can drive down the road, but you don't know exactly how the engine works. Working memory is similar in this fashion, and it's split up into 3 main parts. These areas include the phonological loop, the episodic buffer, and the visual spatial sketchpad. First off, let's get to the phonological loop. So the phonological loop handles all of the auditory information. Within this loop are the areas of the brain that process what we hear and rehearse what we are going to say. When people are asked to memorize a phone number or a set of words, the phonological loop is put in charge. And it's called a loop because if the loop is too long, you can't start the process over. For example, try to remember these numbers. 56273. You can say them in your head over and over. 56273, 56273. Now, close your eyes and try to say those 5 numbers again. You probably did it, right? Now, try to remember these numbers. 5627328158924. You can't remember that, can you? That's because it's too long to fit inside of the phonological loop. By the time you get to the very first 8, you've already forgotten the first number. And something else that's interesting about the phonological loop is that it's not about the numbers. It's about the length of time in which you can say those numbers. Some psychologists cut it off at 2 seconds. And it's very important to remember that not all languages are actually perfectly efficient. For example, in some languages, it could take you 2 seconds to say 5 digits, while in other languages, you could say a whole 10 digits in 2 seconds. It's also important to note that the phonological loop can also hold visual information like pictures that is then turned into semantic information like words. For example, if you see a sign that says "slow down, turtles ahead," you can turn that visual information into auditory information by saying the phrase in your head. Now let's move on to the second part of working memory, which is a visual spatial sketchpad. So now we know what's in charge of what we hear, but what about what we actually see? The images that we take in and create in our mind are all handled by the visual spatial sketchpad. So try to think of a map from your house to your best friend's house. You're probably seeing a top-down map with a line across each one of the roads to get there. This place in your brain is called the visual spatial sketchpad. Colors, shapes, even haptic feedback are all information that is stored in our so-called mind's doodle book. And the visual spatial sketchpad is pretty simple. Let's move on to number 3, the episodic buffer. So we've got numbers and words in the phonological loop, and we've got pictures and images in our visual spatial sketchpad. But how do we connect these two? Well, according to this theory, we use a third part of our working memory called the episodic buffer. The episodic buffer is the area of your brain that adds the soundtracks to the visuals and subtitles, so to say. Like a movie, it puts together visual and auditory information and adds a sense of timing and organization. So just like single words can make sense alone, you need to put them together to convey even more information. Some psychologists say the episodic buffer also integrates time into each. So now that we've gone over the phonological loop, the visual spatial sketchpad, and the episodic buffer, let's go into some more stuff. For example, how is working memory and intelligence correlated? Well, if you've got a good working memory, you should be quite pleased with yourself. According to Peter Doolittle, people with good working memories tend to be good storytellers and also score higher on standardized tests. A good working memory allows someone to remember information while recalling other pieces of information or performing other functions. And while more research still has to be done, many experts say that working memory is a good predictor of general intelligence. In fact, according to a few other studies, working memory and intelligence seem to be very closely correlated. If working memory is your ability to manipulate information, and intelligence is your ability to solve complex problems, it would make sense that having a higher ability to manipulate information should allow you to solve complex problems better. So, what about measuring working memory? Well, there are 3 main tests. The first one is called an in-back test. An in-back test is a very simple test that goes like this. First off, I will tell you three numbers, 4, 6, 2. Then what I'll do is I'll have you tell me what the number was 2 numbers ago. For this example, the answer would be 6. Then I'm going to tell you another number, 8. Now you have to remember all those past numbers, and you have to tell me what the number was 2 numbers ago again. This answer again would be 2. Then I'll add another number, 4, and then I tell you to give me the number 1 number ago. And now it would be 4. Then let's say I give you another number, 9, and I can tell you to go all the way back to 3 numbers ago. Can you remember it? The answer would be 8. And as you can see, this task can get very difficult simply going from 1 to 3, and most people can't make it past 5. However, that's the in-back test, and psychologists use it to measure working memories often. Secondly, we have something called a calculation test. This is when you need to perform a calculation on a set of numbers. We can do a very easy one. Let's say that I give you 3 numbers, 6, 3, and 2. Now, I just need to ask you to add 2 to each number. So for this example, the answer would be 8, 5, and 4. And if for some reason a large percentage of the population achieves this, it means it's too easy, so we can make it more difficult. Let's say I give you 9, 5, 7, 2, and I ask you to double each of these. The answer would be 18, 10, 14, and 4. And lastly, we have something called a rotation test. You can see very clearly how the in-back test and the calculation test measure your working memory capacity in terms of only the phonological loop, using numbers and stuff, right? But what about testing your visual spatial sketch pad? Well, we have something called the rotation test. This one is pretty difficult to explain, but it's kind of like this. I show you an image of a three-dimensional object. Then, I give you a few different rotations of that object, and one of them is an impossible rotation and it won't match the original, no matter how you rotate it. Then I ask you to find that impossible match and select it. It seems as simple as that, right? Well, it's actually sometimes pretty difficult. As I end this video, I want to let you know that I just
All right, I'm going to stop it there. Apologies to this guy. We're not going to take his test. Nothing personal. Okay, so again, that was just really sort of a brief overview. So let's talk about each of these parts in Badley and Hitch's model of working memory in more detail. So starting with the central executive. And again, remember that these are all sort of these hypothetical ideas, although we do have empirical evidence from research studies and also neuroimaging, and we'll talk about that throughout the lecture. But first of all, the proposed central executive mechanism, it's really kind of this command and control center that presides over and coordinates the interactions between the phonological loop and the visual spatial sketchpad. And so what it does is it's really like a conductor, honestly. And so it integrates the information that we get from the various components in the model into a more cohesive whole. And so it also plays a role in focusing our attention, helping us to plan and to select strategies to make the best kinds of responses we can to things in our environment. It helps us to transform information, coordinates our behavior, and it also helps us to suppress irrelevant information, or to suppress our attention to irrelevant information. So it's really keeping us on track. And so despite all of these different activities, I want to make it clear that it doesn't store information. It's really just in charge of, moment to moment. Okay, you do this, you go over here, but it's not retaining any of the information that's coming in from the sensory stores. And finally, much like the vast majority, probably all of our cognitive processes, it is limited, right? We're limited in our cognitive resources and energy, and this of course trickles down to the central executive as well. So it is possible for the central executive to kind of get overloaded. It's not going to be perfectly coordinating any and all tasks that you give it. There are going to be limits to what it's able to do based on available cognitive resources. And so the next system that we're going to talk about is the phonological loop. And so this is a hypothesized mechanism for acoustically or auditorily coding information into our working memory. And this means that because it is specific to acoustic information, it is modality specific. That is, it only processes information that is in an auditory format. And so the evidence for this kind of modality specificity, it came from studies that asked participants to recall strings of consonants. A notable study in this realm is one by Conrad and Hull in 1964. And so what they did in this study is that they showed participants two kinds of lists of letters in the English alphabet. And so the participants were seeing these letter lists. And so some of the lists had letters that had similar sounding names. So like C, T, D, G, V, B. And then the other kind of list had this really dissimilar sounding letters. So they don't sound anything alike, like C, W, Q, K, R, X. And so what they found was that participants, they correctly recalled more letters from the second list, the dissimilar sounding list, where the sounds were different between the letters. And so this pattern of recall errors with the similar sounding letters, it indicated that, well, perhaps the letters weren't visually coded in the short term. So even though they were presenting these letters in a visual format, it seemed like, well, there must be something verbally going on in our working memory. There must be some sort of translation of this visual information into this auditory information. And so this is because people took the visual stimuli, like I said, and then sort of translated them based on the sounds that they make. And so in line with this idea is the evidence that we briefly talked about when talking about like our short-term memory, is that our immediate recall for lists of words is a lot worse when a lot of the words on the list sound similar to one another. And this is in comparison to when they sound dissimilar. So again, kind of this idea of this like rhyming quality confusing us and making recall more difficult. And this is the case even when the words that are not similar to each other in sound are similar in meaning. So you have words that are similar in meaning but don't rhyme, essentially, and people are better able to recall those than words that aren't similar in meaning but do rhyme. And so this finding then indicates that there is this acoustic code, there is this sound-based code that is used in the mind versus a semantic or a meaning-based code. And this is because these words that sound similar, they interfere with each other, whereas these words that are related by their meaning, they don't interfere with each other. And so the phonological loop is thought to have like these two different parts. So one is this short-lived acoustic store or phonological store, and this hangs on to sound inputs. So again, just really more of like this idea of just a more basic like holding cell or holding tank, storehouse for this auditory input. And then we have this sort of articulatory component. And this is thought to play a role in what's called the subvocal rehearsal, essentially saying the words back to yourself or saying the letters back to yourself in your head. And it's without this articulatory control system, we're not able to rehearse. We're not able to say, okay, so the words on the list were bread, dog, sugar, tea. We're not able to kind of have that internal like echo chamber happening. Um, and because rehearsal takes time, the span of time in which the phonological loop can hold information is obviously limited, right? So like he talked about in the video, when we are trying to rehearse things, there's only so much that the loop can hold on to. There's only so much rehearsing we can do before time, just like a natural enemy of memory, starts to decay that information. Um, and this phonological loop, it serves a number of purposes, as you can imagine. Obviously, we're animals who use sound and language to communicate with one another. And so, this loop is active when we count, when we read. It plays a role when we are working to acquire new vocabulary words, whether that's in our native language or if you're trying to learn a second, third, etc., additional language. It also plays a role when we are trying to keep track of instructions for more complex tasks over like a more extended period of time. So, for example, when you are taking a test in person, if the professor's like, okay, here is a Scantron, you need to use a number 2 pencil, make sure you bubble in your name and your ID number, make sure that you do this and that, put your name on the various pages of the test, things like that. In that case, the phonological loop is not only holding on to that information, but then repeating it so that you are aware of what you're supposed to be doing as you go through the test. And so next, we are going to talk about the visual spatial sketchpad. So this is an aspect of working memory that essentially it parallels the phonological loop. So it has a similar sort of function and process, but of course it's just using visual and spatial information, or it's coding that. And so not only like the like features that you can see, is something like shiny, dull, what color it is, things like that, but also the three-dimensional information that we get from our surroundings as well. And also, like the phonological loop, the visual sketchpad is also limited in its capacity. And this component is responsible for holding on to visual information for objects, landmarks, people, and also helping us to navigate from one location to the other. And we also use it in leisure activities where we're interacting with and manipulating objects. So like playing video games, doing jigsaw puzzles, solving mazes, and things like that. So there has been a lot of empirical evidence that has suggested to us that the phonological loop and the visual spatial sketchpad are these two independent yet interacting collaborative components in the working memory model. And so one such study that really helped us to differentiate, it's not that short-term memory can just on its own process all of these things, but actually it's more complex. It needs to be broken down into this more nuanced process of working memory, right? Where it can not only be holding and manipulating things, but then it also has specific codes for specific modalities, right? Where it's like, okay, it can take in visual information and it codes it in a certain way. It can take in auditory information and code that in a certain way. And so this study by Luck and Vogel, it was looking at working memory ability for the features of objects. So things like the color of an object, its orientation or angle in space. Um, and it was also looking at working memory for objects that contained these sorts of features as well. So the features just sort of on their own as just isolated factors, and then also the combination of these different factors. So the color and the orientation and the shape and da 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 da. And so based on their results, they found that our visual working memory can hold about 4 items at any one time as we're trying to manipulate them. And they also found that up to 16 different features can then be held onto by our working memory. And this is because of chunking. So in this case, if we were to combine the different features, right? So like a green horizontal bar, right? We have the color, we have the orientation, it's horizontal, and we have the shape, it's a bar. And so chunking then helps us hang on to more of that information rather than sort of splitting it off into its own. And so this finding about visual working memory and its capacity, then it means that the visual spatial sketchpad must have similar underlying principles and functions as the phonological loop, since they have this similar sort of capacity. But it's something that is specialized for purely visual information. So again, this idea that you have these two independent processes, but they are working with different kinds of information. And so another study was done by Logie, Zuko, and Badley, again, Badley. And so they conducted a study that was looking at whether different modalities, that is visual and verbal, interrupted one another, or if they were essentially separate. So do they have this sort of negative impact on one another, or do they operate in ways that show that like they're separate, they're doing their own thing? And so the rationale for this, or sort of their theory behind setting up this study, was that, well, you know, if there are two working memories, if there is a visual working memory and a verbal working memory that are then independent of one another, then having to complete a visual task while you're using verbal memory, that shouldn't cause a problem. Whereas there will be a problem if you're completing a visual task and using visual working memory. And similar sort of thing for if you're doing a verbal task and using visual working memory. So this idea of these different modalities, are they interfering with one another or not? And so this is exactly what researchers found. What they expected is what they found. So they found that when you are engaged in a task using one modality, but then you are using your working memory to do a different modality. So let's say you were like doing a task where you had to sort blocks, right, into like maybe different groups based on like, oh, their size or their color or something like that. So you're doing this visual task, and then you were asked maybe to verbally count out loud backwards by 5 from a random number, 136. That you were a lot better equipped to be able, you were able to do both of those things simultaneously. Whereas if you were doing a verbal task, maybe a verbal version of that, you know, maybe having to like identify the colors of the blocks, and then do a like mental arithmetic task, that it would actually be harder, because that would be you'd be infringing on that particular part of working memory with this new task. So essentially you'd just be overloading either the phonological loop or the visual spatial sketchpad with even more information than it already had. And so Yeah, and so this pattern of performance then it can't be explained by this assumption that, well, there's just this, short-term memory system. It's really basic. It holds information and then it moves it on to long-term memory, like we saw in the modal model of memory. But rather that we have this more complex working memory system that has these component parts that specialize in holding and manipulating verbal and visual information. So now we're going to move on and talk about the episodic buffer. So this was the latest addition to Badley and Hitch's working memory model. And this is essentially a temporary storehouse where we can gather and combine information from the phonological loop, the visual spatial sketchpad, and also our working memory. And so essentially, this allows us to integrate auditory, visual, 3D information with our long-term memory. So the episodic buffer is not only letting us hold and manipulate information that is relevant to the present moment, but it also lets us have this sort of continuity of experiences by pulling on long-term memory, by pulling in our past experiences as well. And so like the other subsystems in Badley and Hitch's model, it also has a limited capacity. We're just continuing to see this, oh, humans have limits, okay. And obviously it is able to process both verbal and visual spatial information. So it's really versatile. And it's also a temporary memory storage system. But its purpose is to really actively manipulate information so that you might be able to interpret an earlier experience. So something that you experienced in the past might then come into play in the present moment of like, oh, this is information that like pertains to like what happened last week, of like, oh, okay, like I'm building on that, right? Like your memory for what we talked about in like previous lectures. You're building on that, and there's a sense of continuity of like, okay, like this is ongoing. This relates to things that I've experienced in the past. It also helps you to solve new problems. It helps you to plan future activities, right? Again, you're able to draw on your past experiences of like, okay, well, what worked before, what didn't? And it then also facilitates the storage of information in working memory to then long-term memory. And so the evidence that we have for the existence of these hypothesized working memory mechanisms, like I alluded to earlier, they mostly come from neuroimaging studies and also cases of brain damage as well. And so through a lot of the research that has come out of neuroimaging, it's mostly been with PET scans. Can anybody tell me, how does a PET scan work? Does anyone remember? So a PET scan, it's one of the neuroimaging tests that we can use to look at brain activity. And so the way that it does this is essentially the person who's undergoing the PET scan has like this glucose, so this like sugar sort of solution injected into their veins. And there's also like a radioactive tracer. It's not like a harmful radioactive. They're not like, here's a bunch of uranium. But it's just a way to be able to track along with that glucose. Okay, where is that glucose going? And so they can then see the uptake, the use of that glucose in the brain. And the idea is, well, the more glucose that is being consumed, the more brain activity is happening in that area. And so These PET scans have then allowed researchers to find evidence for more distinct brain areas that are involved in the different components of working memory. So really being able to pinpoint, oh, okay, these are the areas in the brain that are becoming more active when this aspect of working memory is being tested. And so they found that the phonological loop, so it involves the bilateral activation, so activation of both sides of the frontal and the parietal lobes. The occipital and the right frontal lobes are responsible for shorter intervals of retention for visual information. And this makes sense, right? We know that the occipital lobe is highly involved in vision, and we also know that, well, the frontal lobe is involved in executive functioning. So then we can also see the role that the central executive is having as it's directing the visual spatial sketchpad functions. And then if there's a longer period of time in which you have to hold on to visual memory, visual information in your working memory, then we see that the activity starts to shift and we use different parts of the brain. So it switches from the right frontal to then the left frontal if there's more time that's needed. And then it goes from the occipital to the parietal. So there's really, it kind of suggests like this rich network in the brain that's involved in our working memory, especially as it pertains to the amount of time that's needed. And then, of course, like I said, the central executive is highly associated with activity in the frontal lobe, right? And we know this because this is where the CEO of the brain lies, right? And the central executive is essentially the CEO or the conductor of our working memory. And then finally, the episodic buffer operations have seemed to involve the bilateral frontal lobes. So again, the right and left frontal lobes, and then parts of the temporal lobe. And this also includes the left hippocampus. And again, this is something else that makes sense as well. So does anyone know or remember what the hippocampus is primarily involved in cognitively?
It's for memory, right? Like
Yeah.
long term.
Yeah, long term. You guys got it. So again, this makes sense that the episodic buffer is not only holding and helping to integrate the information from the phonological loop and the visual spatial sketchpad, but it's also reaching into long-term memory, so involving the hippocampus to then better make sense of that information that it's manipulating. Great. And then regarding the evidence that we have from cases of brain damage too, the book begins the chapter with this famous example of an Italian woman called PV, her initials, and she had suffered a left-sided stroke. And so this had then damaged her parietal and temporal lobes. So a large amount of the brain here, the upper part and then the side on the left side. And so because of this, her verbal short-term memory, she could only hold one piece of information at a time. So she could only hang on to one number or one word at a time. So the stroke had then had impaired her verbal working memory. But she still had it seemed like a untouched visual working memory. It seemed like that didn't get impacted by the stroke because she was able to remember about 6 items. So she was able to hold and manipulate about 6 items of information in her visual working memory. Also of note, her long-term memories were intact. So she wasn't having any difficulty recalling her past experiences. And so because of this pattern of working memory abilities and long-term memory abilities that this woman demonstrated, this is actually what encouraged Badley to rework the theory and to add in the episodic buffer. And the reasoning for this was that Badley thought, well, maybe this episodic buffer is what's providing the link for the phonological loop and long-term memory. So again, going back to the different models and understandings of short-term memory, we know that there's already a limit to our short-term memory, right? That idea of there being this bottleneck, there being this slowdown. And so with this woman, there's even more of that bottleneck. Only one piece of information was in short-term memory and then being moved over to long-term memory at a time. But she was still able to not only remember this information in her long-term, but also pull out past long-term memory and then engage with content in her working memory, verbal content in her working memory in that moment. And so again, this suggested, well, there's something else that's going on aside from just the phonological loop and the visual spatial sketchpad. So we're just going to end real quick, just talking about working memory and attention. And so it's really important to note that, as is the case with all of our cognitive functions, right, that working memory, it's not just working memory is happening in isolation. You're given a math problem and the working memory parts of your brain fire up and everything else just like goes offline. And so working memory and all of our different cognitive functions, they're constantly working together with other ways of thinking. And this is really notable when it comes to working memory and attention. And so the more that your working memory is having to juggle, the less attentional resources you have to pay to other information. And so the focus on this attention research and its connection to working memory more recently has been on, well, how do our visual systems process multiple stimuli? How do we process multiple stimuli in just sort of our day-to-day, our typical scenes? And then how do we select relevant or important objects from the many pieces of information that are constantly coming at us? And so some researchers by the name of Levy, Hurst, de Fochtert, and Viding in 2004, they hypothesized that there are two mechanisms of selective attention that are involved in, that are selective attention that then has implications for our working memory. And so the first mechanism is this idea that there's this perceptual selection mechanism. And so this is helping us to exclude or reject distractions from our visual perception, but it's based on really shallow processing. So just really basic processing. So it's not doing anything in depth. It's really just more of, is that thing the color red? Yes or no? And so this mechanism is happening when our perceptual load is really high, right? So we're juggling a lot on our mind. We don't have that much attention we can to direct to other visual stimuli in our environment. So therefore, we're really kind of like just cutting corners, essentially. We're not able to pay a lot of attention. So we have to use more shallow processing. And so this mechanism is supposedly passive. because, like I said, there's just not a lot of capacity in the attentional system when we're juggling a lot in our working memory. And it's also thought that this filtering process, it takes place um, by a mechanism early on in the information um, uh, input process. Um, so there's a lot of things going on. You're just kind of taking shortcuts to say yes or no, yes or no. And then it's happening pretty early on as you are having that information come into your brain. And then the second mechanism that they proposed is what's called the attentional control mechanism. And so this interacts with distractors in a more nuanced sort of way. So rather than having this more shallow processing approach, it's able to take a more detailed processing approach, what we call this deep processing. So you are able to evaluate even further the various features of a stimulus and object that you're seeing. And this then is able to occur under conditions where we don't really have a lot going on in our working memory, what we call a low perceptual load, which makes sense, right? This trade-off of, well, okay, if there's not a lot that we're juggling, there's more that we can pay attention to. This mechanism's job is it's a really active one. Again, there's more attentional resources when we don't have so much up in the air in our working memory. So it has the energy to be a lot more active in its more deep dive of processing that's happening. And then in contrast to the perceptual mechanism that I just talked about, this kicks on later on in the perception process. So I know that we are at time, but does anybody have any questions about what we've talked about today?